So our next speaker is Thomas Lamb, mirror symmetry for black varieties via the Langlands program.
Thank you for the introduction, and I'd like to thank the organizers for inviting me to speak. It's my first time at the center, and I'm enjoying it a lot. So my talk is joint work with Nicolas Templier. And first, I would like to apologize that there's no symplectic topology in my talk. Hopefully someone will tell me how to put it in. The version of a mirror theorem that I'm going to talk about is an old one due to given tau. Let me recall how it works. So it's for final varieties. So we take a final variety and we consider its quantum connection, which I'll think of as this H-bar connection. And this is multiplication in small quantum cohomology. I'm only going to talk about small quantum cohomology. And I'm only going to have my quantum connection in one direction. I'll take sigma, this class here is a generator of this group. So all the examples I talk about have the feature that this thing has dimension equals 1. If this group has higher dimension, then the connection that I want to look at would be in the anti-canonical direction, but divided by the final index. Anyway, so for us, we can just take a generator for this group for all the final varieties I talk about. And this is on the A side. And on the B side, the kind of thing we talk about is a Landau-Ginzburg model. And for me, that's the following data. We have X is a complex variety, affine. And we're given a holomorphic function. And we'll also have a sort of projection down to C star. And we think of the coordinate on C star as the quantum parameter.
So X equals 10 over X is different from 10. It's just some general.
Yeah, so this is the Landau-Ginzburg model. Hypothetically, we need to separately construct this.
Correct. Yeah. It's mirror.
Okay, and on this left-hand side, we consider some integral functions, which are functions on this base, and they have the following forms. So this function is defined to be the integral of e to the f, e to the superpotential, over some real cycles that live in the fibers of this. So these real cycles will be their real dimension will be equal to the complex dimension of the fibers, and this is some holomorphic form which I won't talk much about. Holomorphic top form. Top form on the fibers of pi. And so given tau cause this data mirror to this, if this function is a solution to this. Solutions. Okay, so I think this is now by now quite old, maybe even like 20 years old. And our theorem is that this conjecture, meaning I can construct this Landau-Ginzburg model, exists. It works for a class of finite varieties called minuscule flag varieties. So I won't give the definition of minuscule flag variety, but I'll give you examples. So, e.g., you can take any projective space, or more generally, you can take any Grassmannian. You can take even dimensional quadrics. You can take orthogonal Grassmannians, and there are some more, some exceptional ones. Previously, Reach had written down this data and conjectured that it satisfied given Tao's mirror theorem. Okay. To simplify things a little bit, for the rest of the talk, I'm going to ignore H bar. And then this is this thing here just defines a connection. So on the trivial so it's a connection on a trivial bundle over a one-dimensional base. That's what it is. And our idea is to think of both sides as D-modules on this one-dimensional base, which is a curve, and apply the geometric Langlands correspondence. So let me draw a picture, sort of overview of the objects that come up in the proof. So the proof is quite indirect, and So the proof relies on studying 4 different D-modules. 2 of them are the D-modules in here. So there's a D-module coming from the connection. In a moment, I'll write down the D-module coming from here. But it's the D-module whose solutions are these integral functions. So these are the 2 D-modules. This is some jargon to describe what Reach wrote down for here. So I won't explain all the words here. So this thing. This is the mirror theorem. So each of these 4 squares is a D-module on C star, or a D-module on P1. The bottom line here are 2 D-modules, and we can basically think of this isomorphism as an instance of the geometric Langlands correspondence. And the specific case that we use is the theorem of Xinwen-Zhu. And so what we do is we compare compare these D-modules on both sides. So this is the A model side, B model. And I'm going to call this automorphic because the definition of it is it comes from an automorphic construction, and I'll call this Galois because it basically lives on the other side of the geometric Langlands correspondence. Okay, right, so this thing is defined by Dubrovin in sort of vast generality. This geometrical crystal thing, this name comes from work of Bernstein and Karstein, and sort of completely independently, without realizing that it was important in representation theory, Reach had written down something that looked the same for exactly the purpose of mirror symmetry. And this character D-module is something I defined with Nicolas. This Kloosterman D-module is rather recent. Actually, both of these things are rather recent inventions, like in the last 10 years. This is something Frankel Gross studied, and this is something that was defined by Heimoff, No, and Yun. Okay. So the mirror theorem is there, and this is basically geometric Langlands. Okay, so in this talk, I'll mainly focus on the left-hand side, so I'll try to explain where a picture like this will come up in the automorphic construction over here. The right-hand side, I won't talk much about, so I'll just say one thing. So to compare these two things, it turns out that this thing is representation theory, and this is quantum Schubert calculus. So there are enough things known about Gromov-Witten invariance for flat varieties that we have enough numbers here. And over here, what we do is we do a calculation involving the canonical basis of some representation. So the calculation here is explicit. One side is Schubert calculus, the other side is representation theory, and somehow in the minuscule case, we know enough that we can just compare the numbers. But somehow this side is more conceptual, and that's the side I'd like to explain.
By minuscule representation, you mean the weights are all congruent under the Weil group?
Yes. Everything is all the weights are in the Weil group orbit of the highest weight. So I'll try to explain how we came up with this kind of automorphic construction of the Landau-Ginzburg model by starting with a case which I think everyone in this room probably knows well, which is the projective space case. So in my notation, there's an algebraic group and reductive algebraic group in this GLN, and the minuscule flat variety, the final variety I'm interested in is just projective space. And what is the quantum connection? So this is M. So it's the following system of linear differential equations. Connection. And this system is equivalent to a higher order differential equation, which is this one, and it's a hypergeometric differential equation. In the n equals 2 case, which is P1, this is the solutions are Bessel functions, so they're very classical things. What is the B model in this case? I'm going to write it in the following way. So there's a superpotential and something that I think of as a projection, the fibers of which I'm interested in. And the map sends this to Q to the product. So the superpotential is the sum, and this projection is the product. As an aside, for those of you who know group geometry, so if we take in general, what this picture would look like is there's a diagram which looks roughly like this, which is that this C to the n is replaced by something looking like this. This is something called open projected Richardson variety in G mod P. This is a log Calabi-Yau sitting inside the Langlands flag variety to the final variety I started with. So those are what the fibers look like. The fibers are these log Calabi-Yau sitting inside the Langlands flag variety. Okay. But anyway, this case, I'm going to focus on the projective space case, which somehow is already kind of interesting for what I want to talk about. And then we write down, so we follow the prescription and we write down these integral functions. So we have to write e to the f. And there's a natural top form of the fibers where basically I write down some natural top form, and I have to integrate over a fiber of this thing. So I have to find some cycle contained inside the set where x such that Q. Just to rewrite it slightly so that it's maybe a little bit more familiar. We can, using this equation, we can eliminate one of the variables, and now that it'll look maybe slightly more familiar. And we have to integrate over some cycle. Actually, it turns out for a long time I was trying to think about these integral functions for general G mod P, and then I didn't understand anything about the cycles, and so somehow the approach we take we don't have to understand what cycles to take. But for example, in the P1 case, the integral is something. It's something looking like this, and sort of basis of cycles to take would be you can take just the negative real line as one of the cycles. Another one is to take take a circle in the complex domain around the origin, and those will give you two integral functions which span the space of solutions to the Bessel differential equation.
So you're telling us that you just care about the differential equations. You're not looking at how the mirror map relates these cycles to quantum homology classes and others.
So somehow the mirror map, because so if we work equivariantly, which I didn't talk about, if we work equivariantly, the quantum cohomology is kind of generated by the divisor class. So somehow to determine the mirror map, you only need to know the image of one class, which we can sort of by an ad hoc way kind of determine. So in some sense, we do know the mirror map, but not the proof doesn't immediately give the mirror map, but you calculate it afterwards somehow because so if you so somehow the quantum cohomology of these things the H2 is one-dimensional, but if we do things equivariantly, it will generate the equivariant cohomology ring. So if we want to do things equivariantly, we insert some polynomial factors inside here, and it also fits in, but I think it's sort of sort of a complication that's better to avoid for the talk. Okay. One comment is which I don't know if it's familiar, is that these things, it turns out in the G-mod-P case, these things can be tropicalized. And when you tropicalize them, they turn into characters of a group. That's why these Landau-Ginzburg models we call geometric crystals. This is some integral function. When you tropicalize it, turns into a sum over a lattice, and that sum turns out to be an irreducible character. Okay. Anyway, that's an aside. So our idea was we can take this picture, and actually I wrote Cn here, but actually the whole thing is sort of all the maps are defined over Z, and you can base change. And we just do exactly. And the maps are the same. So given some coordinates here, that maps to the sum. And given some coordinates here, it maps to the product. What's the finite field analog of writing down this function? It's writing down something called an exponential sum. Right. So actually, it's a little bit dangerous to use Q when working over finite fields. So I'm gonna change this. So Q is the quantum parameter if I'm in the theorem setting. Okay. In finite characteristic, let's call A. So given some point in this finite field, we'll define the following summation. The sign should probably be ignored. Now it's not important. So what we do is we take this summation and we replace it by a sum, and we just put in instead of e to the f, I take this exponential 2 pi over p. So this is some character. This thing is some character on ft, and that takes the role of this exponential function. And one good thing about this trigonometric sum is that you don't need to pick a form to integrate over, and you don't need to pick any cycles. So there are fewer choices here. There's actually only there is a choice of which character to pick. You could pick, you could sort of multiply by k, 2 pi k I over b. But other than that, there are no choices. You just sum over all the points in the fiber. You don't have to choose a cycle. So this trigonometric sum has been around for a while. It's called the Kloosterman sum. So it's been around for around 100 years. And it's apparently kind of important in analytic number theory. So this is, and there's a version of this with fq instead of fp, where q is a prime power, where you keep the same character, but you add trace here in front. Anyway, the first main theorem about the Kloosterman sum for us is the Way-Deligne band. So if we allow the finite field to vary, and you also have, then these Kloosterman sums are bounded by some explicit band. And this band on the right hand side is roughly the square root of what this sum could potentially be. So these things are all things which lie on the unit circle. If you sum them over, then the biggest size let's say, the absolute value of this is less than or equal to this. So you sum a bunch of things which are all lying on the unit circle, and so the number of things you sum over would be sort of a possible estimate for the sum. But basically the bound is that it's around square root of the naive size. And to explain this property, Deligne gave a sheaf theoretic interpretation of this trigonometric sum. So around the 1970s, this is SGA 4.5. Deligne defined this thing called a Kloosterman sheaf. So my notation is kind of the same. This sum I denote by KLN. The sheaf is also KLN, but I write QL bar to show you that it's a QL bar sheaf. And it's defined to be by a push-pull. In this picture, we start with something called the Artin-Schreier sheaf. We pull it back and we push it forward, and that's the construction. So here, I'll say a little bit more in how we think about this thing. And this is a degree shift. It's just a convention. We can ignore that. Deligne's theorem is that under the function sheaf correspondence, this sheaf corresponds to this function over there. And so just to write it precisely, it's right. So sorry, this is a sheaf on this base here. Let's write GM. And all right, so if we just take the trace of Frobenius on the stalks, we'll end up with some number in here. So we need to choose an identification of QL bar with complex numbers to compare with that thing, which is a complex number. How should we think about Artin-Schreier sheaf? So under the function sheaf correspondence, this Artin-Schreier sheaf corresponds to this function, 2 pi I over p question mark. So under this trace of Frobenius thing, this Artin-Schreier sheaf corresponds to that. And so when you pull it back, it corresponds to this function. And finally, the hardest part is to push forward this sheaf. So there's an analogous thing we can do with integral functions, which is to replace everything with D-modules, but use the same symbols for D-modules. So the analogy in the is to define this Kloosterman D-module will be defined by exactly the same symbols, but instead of this Artin-Schreier sheaf, we take something called the exponential D-module. So here, x, you can basically think of it as the exponential D-module. So this is some D-module on C or A1. This is the D-module whose solutions are e to the x. So the exponential D-module has solution e to the x. if you pull back the exponential D-module, then that has solutions e to the f of x. And if you push it forward, then that corresponds to integrating. Sort of, roughly speaking. So here's a game you can play whenever you have a Landau-Ginzburg model. One game you can play is you can just base change, if possible, if the holomorphic function is sort of defined over Z, you can base change the finite field and consider these trigonometric sums and these analytic sheaves. Another game you can play whenever you have a Landau-Ginzburg model is you can just write down this D module, this push-pull. And so, what Deline does is he proves a bunch of basic properties about this sheaf. So because of this degree shift, it turns out that this thing, which a priori is a complex of sheaves because it's of the derived functor, is actually concentrated in 1 degree. It turns out to be a local system, which is not obvious. So this says that somehow the fibers are kind of constant. And it has the rank that we expect. So n is the dimension of the cohomology of Pn minus 1. So somehow that's what the n is here. And he thinking of this sheaf on P1, you can ask about its monodromy at 0 and infinity, where it's singular. So it's a local system so it's least on GM, but at 0 and infinity there's some interesting behavior, and he computed what this behavior was. It's tamely ramified at 0 with maximal unipotent monodromy. It's totally wildly ramified at infinity, and the Swan conductor is equal to 1. And the fourth statement is that it's a pure sheaf of weight n minus 1. So this statement 4 corresponds to this band. So that the purity is what gives these bands. Though there won't be, the purity is was one of the main things that Deline was interested in, but somehow not obviously, not obviously so important for us. Tamely ramified corresponds to regular singularities of the differential equation. Wildly ramified corresponds to irregular singularities, and this Swan conductor corresponds to the notion of irregularity of a system of differential equations. So one interesting feature of computing these two local ramification behavior is later on Katz showed something rather surprising, is that actually there's only basically one sheaf which satisfies these two properties. This KL and QL bar is rigid, which in general means that it's determined by its local ramifications. But actually, in this case, it's somehow even stronger than that. Just these two properties, 2 plus 3 determines the sheaf. Up to sort of a translation on GM. And sort of ultimately, the proof doesn't go via rigidity, but sort of this is the intuitive reason why this case of the mirror theorem is easy in some sense, is why we're able to do something in this case and in the other cases, is somehow if we're working with D-modules, the corresponding D-module is just determined by local monodromy. There's only one D-module with a particular behavior at 0 and infinity.
But if you fix the regularity, it's still unique.
If you fix
The regularity, I mean, if you go by characteristic 0, probably it's still unique if you fix.
so
I think that you don't have an analog character if you're
I'm not entirely sure if these two. I think it's true that any D module which is a connection on GM and satisfies this at 0 and is totally irregular with irregularity 1 at infinity will be the quantum D module of Pn. I think that is true. Though there are some things which are somehow the study of so one thing Katz did was to try to classify rigid local systems and then to try to classify rigid L-laddic sheaves. It's actually a rather recent industry to classify rigid irregular D modules. I think that it's sort of a recent work has been done on this. So I don't know exactly the sort of complete understanding of rigidity in the DRAM setting.
Okay. Are you able to translate for us into the language of quantum cohomology what the words rigid mean?
I don't know. So none of you seem to write the word rigid in your papers. I don't. So somehow, with quantum connections, you try to talk about isomonodromic deformations, and that kind of is orthogonal to rigidity. Like those are two different ways in which you can think about sort of like parameter space of connections. So with isomonodromic deformations, you're asking to deform it by having the same behavior. And here it's saying that actually there's only one object with a particular local behavior. So I haven't seen this, but it's also the other thing I want to say is that this is not true for the quantum. This rigidity statement is not true for the quantum connection of a random final variety. I mean, as stated, it's not true for for example, for the flag variety of GL3, and it's not true in the category of GL local systems, even for minuscule flag varieties. So the rigidity is only true after you reduce the structure group. So there's an additional complication. So for Pn, it's just literally true that the quantum connection is a rigid object. But for, say, the Grassmannian, it's rigid not as a rank dimension of cohomology local system. It's rigid after you reduce the structure group to a smaller group. So there's some complications, and I don't understand which final varieties and should give you quantum connections to this behavior. But I mean, I tried some other ones, and there are some other ones which our theorem doesn't cover, but are actually rigid. So
this reduction to a smaller rank, is it analogous to this middle convolution? describe the region?
So it's analogous to how if you take the, somehow the, so I forget what the name of this is, but if you calculate the quantum connection of projective space and you calculate this, then they're kind of related by exterior power. So, I think it's called, is it called abelian, non-abelian correspondence? So there's some name like that, which says that if you calculated the quantum connection for this thing, you can get this thing by just taking the exterior power of this connection. And basically, the thing that's rigid is this one. After you take the exterior power, is not rigid as a connection over the whole for this dimension, but it comes from something that's rigid. So that's the. I don't know if that answered your question. But yeah. Yeah, so I don't have, say, a conjecture for which quantum connection should be rigid, because somehow the notion of rigidity requires reducing the structure group of the connection, and I don't know how to do that in general. Okay, so this was all done in these things were done in the Helvetic setting in the 70s and 80s, and for my story, the next development happened 30 years later. Around 10 years ago, Gross wrote down an automorphic object that should correspond to this under the Langlands correspondence. So sort of for my story, this is the next thing that happened. So in fact, he didn't quite write down this automorphic representation. Let me have some notation. What he did was he did a trace formula calculation, and he showed that there is a unique automorphic representation satisfying the list of properties I'm going to write down. And the list of properties is exactly the automorphic counterpart of the first three things that Deligne proved. So it's a local system away from the spatial points. It's a particular representation at 0, and then it's another particular representation which actually he simultaneously invented at infinity. And now, so what is an automorphic representation? It's a vector subspace. So it's a subspace of some space of functions on a double quotient. So there's some notation here which isn't so. Important here. So this is the Adels, and we take this group and we construct a double quotient and we look at functions on it, and inside it we find a subspace, and that's what an automorphic representation is. And what Gross did was calculate that there existed a unique subspace with these properties, and this was made geometric by the later work of Heinrich, No, and Ewing. So that this is probably going to be more easy to understand.
Sorry,
Yes.
no, it's just P1, it's projective.
Right. Yes. Yeah. So this is the function field of P1. That's what that is. So what Heinrich, No, and Ewing did, which is around the same time as Grotius, they actually wrote down an explicit function in here and showed that it's a Hecke eigenfunction. So they wrote down. So that's vector inside grosses pi. So that's just some function from this double quotient, which I haven't explained what the notation is here, but in a moment I'll write down something else which might help understand it. So it's just a QL bar function on here with satisfies some properties, and it's the important property is that it's a Hecke eigenfunction. You should think of this thing as some analog. It's a little bit like Kloosterman sum, and you can lift this. You can try to lift this to a sheaf, and that's the next step is that they upgrade to an automorphic sheaf on this. And so what is this thing? So this thing has is the stack of G bundles on P1, but there's some on P1, but there's some extra structure to this which corresponds to. So it's just a bundle. It's just a G bundle on GM. But at 0 and infinity, there's some additional information, and that's the additional information is captured by these groups here. But in terms of bundles, it's captured by a level structure plus some level structure at 0. The level structure at 0 is very simple. It's a flag in the fiber. The level structure at infinity is kind of more complicated. It's sort of is some kind of equivalence class of local trivialization. So it's not that easy to just write down what the meaning of the level structure at infinity is.
So what are the indices? One is 0 and
it's the indices. So the first one is right. So I'm using some notation here, which is that the indices describe how deep the level structure is. And so the first one is at 0, and the second one is at infinity. And somehow
I mean it's 2 or it's infinity. Is it just?
Oh, 2. Yeah, 2. Somehow it's there's a filtration of the group, and how deep you need to go is how it determines the level structure. So somehow if the analogy is what's the order of the pole of the differential equation at 0 and infinity. So at 0, the differential equation is supposed to be regular, so the level structure is not very deep. And at infinity, the order of the pole of the differential equation is order 2, and you have to go a little bit further to be able to describe that irregularity. So that's why the level structure at 0 is kind of regular singularity, and the level structure at infinity is irregular, but sort of still very controlled kind of irregularity.
Second order pole.
Yes, it's a second order pole. Yeah. Okay, and the feature of this thing is if you just take its k points, it's in bijection with this double quotient. So this double quotient, which I actually didn't explain what it is, somehow it's maybe the geometric version of it is that if you take this stack, then the k points are in one-to-one correspondence with this set of double cosets. Okay. So one important feature of adding these level structures, so it's not true if you don't add in these level structures, which is equivalent to adding a regular singularity and a special kind of irregular singularity, is that this bun G0, 2, it's an Artin stack, but it contains inside it a piece which is kind of not that bad, and it was this piece was sort of explicitly used by these guys in the construction. So it contains a piece, an affine open, which is not stacky at all. So a typical bundle, G bundle on P1 will have automorphisms. But after you fix these level structures, you manage to you manage to get a piece of the moduli space which has no automorphisms, and this piece is basically GA to the rank of the group plus 1. So it's just a variety, and it's no longer a stack. And that's kind of basically responsible for why we can explicitly calculate this this automorphic object, is that somehow we can work over the non-stacky part, because Landau-Ginzburg, at least our Landau-Ginzburg models are not stacky. So associated to this moduli stack is something called the Hecke correspondence, which I'll just call it Hecke, and I'm going to try to write it in a way that's somewhat suggestive. So the Hecke correspondence is the space of quadruples where you take 2 points in bund G. So you take 2 of these G bundles. You fix a point on the curve. Our curve in this case is it's either P1 or GM, but let's for this point I'll just let it only be in the nice part, so the GM part, and then I ask for an isomorphism of these bundles away from that point. So that's the data in this Hecke correspondence, and it obviously has a projection where I remember the first bundle, or I remember the second bundle, or I remember the point. And those are my projections to here, here, and here. And the statement that this is a Hecke eigenfunction, this is a Hecke eigenfunction, translates to this being a Hecke eigensheaf. So the result of Hainov-Noah union is that this sheaf, which upgrades the eigenfunction, satisfies the Hecke eigenvalue property. So if you do a pull-push, then you get the same thing. So you pull it back here, and then you push it down. You get a sheaf on here, and what you get is the same sheaf, but times something here. And the thing that you get over that side is the eigenvalue. And they define this thing, the eigenvalue, they define this to be the Kloosterman sheaf for an arbitrary reductive group. So the difference is between what Delis did and what Gross did is what Gross did works for any reductive group. And what they checked is that this thing, if G is equal to GLN, G check is equal to GLN, which is the same as G is equal to GLN, then you recover, and this thing is just what Delis defined earlier. Anyway, they call this the G-check Kloosterman sheaf. So that's perhaps the main theorem of Hainov-Noah. And they also checked that it had the nice properties that Delis proved for the GLM case, basically. Okay, so what's our idea? Our idea is what we're going to do is we're going to restrict this diagram to an open piece of it, to a small piece of it. So we're going to look at the part of the Hecke correspondence that maps to, first it maps to the open part here. So I said there's an open part which is just a variety. So we're going to look at the part which maps to that. And we're also going to, so P1 inverse of this nice part of the stack. And then we're also going to fix a particular bundle over here. We're going to take the trivial bundle here, but keep the curve. And so this cuts out a piece of the Hecke correspondence, and you get a diagram which looks like this. And so our main idea is that this is basically a Landau-Ginzburg model. In the case, in this minuscule case, this is a Landau-Ginzburg model. I have to be a little bit careful, so there's some details. Anyway, first of all, everything in this picture will become varieties and no stacks anymore. And you can identify this with the Landau-Ginzburg model after some work. This diagram is of this form. An F, a superpotential, and then a projection down to the curve. So there are some details which I'll mention. So the first thing is it's as I've written it, this is not literally true because actually this thing is infinite dimensional. What we have to do, because this captures not all representations of G check, and so to make it finite dimensional, we have to pick a representation of G check, and we pick the minuscule one. So if we pick something else, we'll get a different kind of picture. We have to intersect with the subfunctor, substack. So inside the Hecke correspondence, you can pick out one which corresponds to a particular representation, where lambda is minuscule, and that will cut this picture down to finite dimensional geometry. And here this function doesn't end up in is not a function, but is a bunch of functions. What you have to do is compose this with a character. So that's the first thing to do, and the second thing to do is compose P1 with the character. And then also base change back to C. But you can see that I'm using notation which suggests that it doesn't matter if we're working over a finite field or we're working over C. So these guys were working over a finite field, but actually all the same definitions work over C. So after cutting this thing down in size, you just get the Landau-Ginzburg model, which was written down by Reach and in the mirror section. Okay. So let me. Before I end my talk, let me say a few comments about kind of things that I would like to think about in this story. So one feature of this is that this Landau-Ginzburg model is actually it's kind of an open piece which naturally sits inside something bigger, and this thing bigger is actually compact. These things are proper. So while Landau-Ginzburg models are affine because they have holomorphic functions, the way it turns out it works in this case is that it naturally sits inside something compact, but the sheaf, the D-module is supported somehow on the open part, on the Landau-Ginzburg model, but it's naturally compactifying. There's something which is studied often in exponential sums, but I don't know if it's studied much in mirror symmetry, is that one of the features is that it's an interesting thing that's often studied is whether this thing here is pure, and I don't know. And this is a question that's often asked for for exponential sums. So there are many Landau-Ginzburg models which are just you take a Laurent polynomial on a torus, and what you can always write down an exponential sum in that case, and you can ask whether you get something pure. And I'm not entirely sure whether there are any mirror predictions for purity. In the other direction, one thing that the mirror theorems have that the Langlands program doesn't have right now is that the D-modules are always graded, because the D-modules act on the cohomology, and the cohomology quantum application is a graded thing. And in our setting, we prove that we get an isomorphism which is graded, but in a kind of ad hoc way. In the Langlands program, this grading seems to be an additional feature, and I don't know which part of the Langlands correspondence can be made graded in the sense that quantum cohomology is a graded thing. So that seems to be something that in the Langlands program is sort of unexpected. In these cases, it was sort of individually noticed that there was like some extra symmetry properties of the objects that came up. And okay, let's stop there. Thank you.
What kind of space is, you said the Hecke space is a compact space, so it's a compactification of this open. Does that find open?
It's
Sorry, you said something.
It's infinite dimensional though. So basically, the fibers are affine Grassmannians. So they're improper varieties. But you have to. So the affine Grassmannian has a stratification by finite dimensional subvarieties, which are sort of indexed by highest weight representations. And you have to choose one of them. We choose the minuscule representation, and then you intersect it, and you get a finite dimensional piece. But basically, all of these are proper in the appropriate sense.
So is it possible to push it beyond the minuscule case?
I've tried. So it's not so obvious because somehow it's already not obvious what to do on the other side, on the Galois side. In the minuscule case, the nice thing is that the dimension of the cohomology of the variety somehow is also equal to the dimension of some representation. But if you take another flank variety, just this vector space on which your D-module is acting is just not the same dimension as any representation. So it's not clear how to get that. Yeah.
More about the strong G0 thing. Like, what's the? What is there any reason that what's the construction and the?
The original reason they defined this bungee zero thing is that they wanted some stack which classified bundles with specified behavior, singular behavior at 0 and infinity. So early on, Deline calculated this Kloosterman sheaf and said it's tamely ramified at 0 with maximal unipotent monodromy, and then it's irregular at infinity. And so the question is, so you have this Langlands correspondence and geometric Langlands correspondence, and you want to ask, can we restrict it to the piece of it with specified ramification behavior? So you've got a huge correspondence, and the monodromy should correspond in some way. So the automorphic representation will have some ramified parts, and they should correspond to the singular places for the Galois object. And so you want to sort of cut down the huge Langlands correspondence into a piece where you just fix this behavior. And you expect it to work because of Katz's theorem, which said there's only one object. So somehow it should be a very small correspondence. That was their idea.
Let's thank the speaker.